Good morning and welcome to our new digital classroom. I hope everybody is nice and comfy in their pajamas like I am. I'm going to be creating videos or finding ones online that are relevant to what we're learning, and we're just going to continue with the next section. So we could have done section 9.9 in one lesson, but I decided to split it up into two and kind of just ease us into this new classroom format. So section 9.9 is titled Representation of Functions by Power Series. And today, the first half of it, we're just going to talk about how do we do this with geometric power series. So let's remind ourselves, first of all, what is a power series? So a power series, if you remember, is the sum from n equals 0 to infinity of a sub n times x minus c to the n. So c is what we say our power series is centered around. So it's the center of our series. And remember the a sub n's are just our coefficients, and those might be functions of n. So when I write this all out, after I evaluate, I get a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared, and the pattern continues. All right. So if I look at this first function here, so consider the function f of x equals 1 over 1 minus x. I can remind myself, hey, this kind of looks like the sum of a geometric series. So if I have a geometric series, which is a times r to the n, the sum of that is going to be a over 1 minus r, where the absolute value of r, remember, is less than 1. Okay, so if I relate that to my function here, I can see that the a value is 1 and the r value is x. So when I put this into a series format, I get that 1 over 1 minus x is going to be the sum from n equals 0 to infinity of 1 times x to the n, which is the same thing as 1 plus x squared plus x cubed plus dot dot dot, where the absolute value of x is less than 1. Okay, so if I want to think about my center for this, I just have x to the n. So that means my center is 0. And I can also see that here, I can look at this and see that my radius of convergence is 1. So putting this together, we say, hey, this is centered at 0, and the radius of convergence is 1, so my interval of convergence is going to be from -1 to 1, and I do not include -1 and 1 simply because I know for geometric series that my inequality is strictly less than, so it does not include the bounds. So what if I wanted to do a geometric power series for that same function, 1 over 1 minus x, but instead of centering it at 0, I want to center it at -1. Okay, so let's talk about that. So what if we centered at -1? What would that look like? Okay, so if I'm centering it at -1, that means I want to have x minus -1 or x plus 1 as the piece that gets raised to the power of n. So somehow I want to get an x plus 1 into my function. Okay, so let's talk about this. So if I have 1 over 1 minus x, we're going to do some algebraic manipulation here. And so the first thing we're going to do is we're going to try and figure out how do I get that x plus 1 in there? Well, if I add 1, so let's talk about this. Let's say here, if I say, okay, I want 1 minus x minus 1, I subtracted 1, so I also need to add 1. Okay, so I subtracted a 1 and added a 1. Okay, And why did I subtract 1? Well, I subtracted 1 because then when I factor out this negative here, I get that x plus 1. So I get 1 over, and then these right here become a 2, and then I'm going to factor out that negative, and then I get x plus 1. All right, so we're almost there. Now my goal is to make it look like a over 1 minus r. So I have the a piece and I have the r piece, but I need this 2 here to be a 1. So what I'm going to do to get that to happen is I'm going to multiply the top and the bottom of this fraction by a half. So once I do that, I get 1/2 over 1 minus x plus 1 over 2. So putting this all together, now I see that my a value equals 1/2, and my r is going to be x plus 1 over 2. And putting this into a series, I get that 1 over 1 minus x is going to be the geometric series from n equals 0 to infinity of 1/2, that's my a value, times my r value, x plus 1 over 2 to the n, where my r value is less than 1, which if I wanted to make this look more like my radius of convergence inequality, I see that x plus 1 is less than 2. So I know that now I have a radius of convergence of 2. And my interval of convergence goes from 1 to 3. Nope, sorry, that is incorrect. The interval of convergence, because my center, remember, is at -1, so I go 1 in each direction, pardon me. So my interval of convergence is -1 minus 2, which is 3, and -1 plus 2, which is 1. There we go. That's correct. All right. Let's talk about some examples. So I recommend that at this point you pause the video, try the example A on your own, and then press play and see how you did. So example A says, find a power series for f of x equals 4 over x plus 2 centered at 0. Great. So if I look at this, remember our geometric series have the sum of a over 1 minus r. So when I relate the pieces of this, I see that a is 4, and oh, well, I don't have a 1 minus r on the denominator, so what am I going to do? We have to do some manipulation here. So if I have 4, I'm going to rewrite this as 2 plus x. And then remember, how did we get that 2 before to be a 1? We multiplied the top and the bottom by a half. So that's what I'm going to do again. Multiply my top and the bottom by a half. And I get 2 over 1 plus x over 2. And I'm going to change that so that it's 1 minus. So 1 minus negative x over 2. Now it looks more like a over 1 minus r. So my a value is 2, and my r value is negative x over 2. And I can rewrite this then as the series from n equals 0 to infinity of a, so 2 times r, negative x over 2 to the n. And if I wanted to write that all out so I can get a better idea of what that looks like, that would be 2 times 1 over x minus 2 plus x squared over 4 minus x cubed over 8. So we get this alternating series here. And it converges for the absolute value of r less than 1, which simply, when I evaluate that absolute value, absolute value of negative x is the same as the absolute value of x, multiply both sides by 2. So I get that the absolute value of x has to be less than 2. And since it's centered at 0, my interval of convergence is going to go from -2 to 2. So another way to do this is to do long division. So it's not fun, but it is doable. And if you always want to check your answer doing long division, you can do it that way. So essentially what we're doing here is we're taking 4 and we're dividing 4 by 2 plus x. And when I look at this, the first thing I do, so I write it as 2 plus x because 4 is a constant, and so I want to look at the constant term. So what do I multiply 2 by to get to 4? I multiply it by 2. And so then 2 times 2 plus x gives me a 4 plus 2x. Subtract that. And I get a -2x. And now I think about what does 2 multiply by to get to -2x? Well, it's a -x. Multiply that to the 2 plus x, and I get a -2x minus x squared. And once again, subtract that, and I'm left with an x squared. What does 2 multiply by to get to x squared? Well, that would be x squared divided by 2. Multiply that to the 2 plus x, and I'm going to get a x squared plus 1 plus x squared over 2. Subtract that, and so on and so forth. And you'll see that you're going to end up with the same series we had over here. Okay, so it's another way to do it. Not necessarily always the easiest, but it is an option. All right, let's try our next example. So once again, if you want to pause the video and try example B on your own, and then press play and see how you did. All right, so for this one, example B says, find a power series for f of x equals 1 over x centered at 1. Okay, so that's the key. So centering it at 1 is the part that can get a little tricky. So what we want to do here is we have 1 over x, and we want to put it in the form a over 1 minus r, but remember in this case we want our r value to be an x minus 1. Okay, because it's r to the n, and we want in our power series x minus 1 to the n. Okay, so that's our goal. We want an x minus 1 to the n for our power series. And in our geometric series, usually we have r to the n. Okay, so how do we do this? Well, the first thing I'm going to do is I know I want 1 minus something. So I'm going to add and subtract 1 to that denominator. Okay, so now I have my 1 minus. The next thing I'm going to do is simply switch the x and the -1. Then I want it to be 1 minus, so I'm going to factor out a negative. So I get 1 minus, and then I'm going to factor out a negative, and I get a, well, actually I'm not even going to factor out a negative. I'm going to write this plus sign here as a plus a negative, if that makes any sense. So I'm going to rewrite this as a 1 over 1 minus a negative x minus 1, right? Because there's an invisible set of parentheses here. So that's what I did there. So now if I look at this, here is my R value. My R value is all of this. And my A value is 1. So if I put this in geometric series form, I have the series from n equals 0 to infinity of A, which is 1, times my R value, which is negative x minus 1 to the n. And that first one doesn't mean anything, but if I distribute this n here to the pieces, I can see that I actually have a alternating geometric series. So n equals 0 to infinity, and then I have a negative 1 to the n, and then an x minus 1 to the n. Okay, so here is the piece that tells me it's centered at 1. And I know that this is a power series because it fits the power series form, and it also fits the geometric series form. So if I was to expand this, I would get that it's 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed plus ... I'm sorry, my dogs are playing in the background. And this is going to converge for my R value, which was x minus 1 less than 1. Which means my interval of convergence, my radius of convergence is 1. Hey, quiet. My radius of convergence is 1, and it's centered at 1, so my interval of convergence is going to be from 0 to 2. Okay, that is all I have for you today. So go ahead and try the couple homework problems. Once you're finished with the homework problems, take a picture of your homework and upload it to the appropriate homework assignment on Schoology. Great, thank you.